Section 10.12, Chaos. When we say chaos in a mathematical sense, we're usually describing some sort of the behavior of some sort of mapping that seems like it should be random, but actually has some sort of underlying order to it. An example of which is Arnold's cat map, which is given by the transformation gamma from R2 to R2, defined by this formula right over here, where xy is sent to x plus y, x plus 2y, modular 1. So in matrix notation, that would be gamma of xy is sent to the matrix 1, 1, 1, 2 times xy modulo 1. Under Arnold's cat map, each pixel point of the unit square, where s is the unit square, defined by the set of points where x goes from 0 to 1, y goes from 0 to 1. So it's just in that, right over here, the upper right quadrant. It's transformed into another pixel point of s. To see why this is so, observe that the image of the pixel point m over p n over p under gamma is given in matrix form by m plus n over p, m plus 2n over p, modulo 1. It's because everything ends up modulo 1 that you end up with fractions for each of the points. As an example, how about we determine the successive iterates of the point 27 over 76, 58 over 76 under Arnold's cat map. So we'll write what the transformation is. It's gamma of m over 76, n over 76. So that's the, oh wait, let me make this a matrix. There we go. And that's the general point we're going to plug in because the bottom is 76, and so that's the p, and then the top will change as we iterate. So this is going to give us this result. So in our case, that's m plus n over 76, m plus 2n over 76 modulo 1. So if we start with the point 27 over 76, 58 over 76, then that'll be our, let's say our 0th iterate. And then we'll plug in, so this will be m, 27 will be m, 58 will be n. So if we take 27 plus 58, then we get 85. But we can't leave it as 85 over 76 because it's modulo 1. So we divide by 76 and we take the remainder. You could split it as 76 over 76 plus 9 over 76 if you want to identify that remainder of 9. In any case, we get 9 over 76. We do something similar for our second part of our point. So instead of doing m plus n, though, we have to take 27 plus 2 times 58, and then see what the remainder is out of 76. So it'll be 67 over 76. And that's our, you could think of maybe your first iterate. So I'll call it 1. And then we'll do it again. So we'll take 9 plus 67, and that actually fits exactly into 76. So it'll be 0 over 76. And then 9 plus 2 times 67 gives us a remainder of 67 over 76. Okay, so that's our second iterate, and then let's keep going. So let's get the third. For the third, we get 67 over 76, 58 over 76, and then 49 over 76, 31 over 76, and let's keep going. We'll get 4 over 76, 35 over 76. And then we'll get 39 over 76, 74 over 76, and then 37 over 76, 35 over 76, and then we'll get 72 over 76 and 31 over 76. And then if we do it again, it turns out we actually get all the way back around to 27 over 76, 58 over 76, and so everything repeats. So we call this a cycle, and because there's 9 iterations inside the cycle, we call it a 9 cycle. So this point 27 over 76, 58 over 76 has period 9. We say that a set D of points in S is dense in S if every circle centered at any point of S encloses points of D, no matter how small the radius of the circle is taken. It can be shown that the rational points are dense in S, and the iterates of most, but not all, of the irrational points are dense in S. A mapping T of S onto itself is said to be chaotic if S contains a dense set of periodic points of the mapping T, and if there is a point in S whose iterates under T are dense in S. So that's our formal definition, really, for what we mean for a mapping to be chaotic.